Hello, welcome back to Python Challenge for All. This is the second part of the summary and review of these sliding puzzle series. So last time we summarized how we make sliding puzzles, like 8 puzzles and 15 puzzles, which are solvable. Solvable meaning that if we slide panels, we can solve it eventually. And then I told you how to solve 8 puzzles only, but manually. So next here, I'd like to show that how we made several tries to solve those puzzles using AI, artificial intelligence strategies. To start with, I showed that some of the puzzles can be solved by making solver function like this. Start the initial value. Yeah, solver function basically does make a list of to-do list, which is called open list. And the initial value is the initial board position or state position. And then we try repeatedly pop something from the open list to see if it is a goal. And then if not, if it is a goal, return it. Otherwise, we check what the successive patterns are, successive board positions are, and put them into make a list of next new states and then put it back to open list and then repeat this process until we get some results or give up. Okay, so there first thing we tried was brute force searches, where we expand the next states and repeatedly try them one by one. But this was not so successful. So next thing we did was best first search algorithms. Best search algorithms are those in which we sort the open list according to some value, some score, and try the very most promising choices first. And the algorithm depends on how we choose the most promising nodes. So here we make sort open list function which sorts the open list according to some value. And here the value is, for example, computed in uniform cost search. It's computed as the number of number of states starting from the length of the path. Okay, the number of states from the starting state to the current path, current state. So this uniform search was good in the sense that it gives good solutions sometimes, and the solutions returned are optimal. But on the other hand, it is not so good. The open list becomes very long, and often it is not solvable. It cannot solve very complicated problems. Then we tried greedy search. In that case, the value is determined only by the heuristics, meaning that in this case, we tried 2 heuristics. This one. Okay, greedy search. So heuristics computed by either number of misplaced panels. If the number of misplaced is small, that's H value is small, so we think that it is closer to the goal. That's called H1 heuristics. And then we tried second one, total Manhattan distance of each panel to the goal position of that panel. And that, I said, is more effective in choosing in calculating the heuristic values, H values. But still, greedy search was not good in a sense that it doesn't return optimal solutions. And then we came to the idea of A-star search, in which we combine the idea of uniform cost search and then greedy search, and then add the both G value and H value computed as F value, and then use this value for sorting as the way to implement best first search. Okay, so and this is called A-star search. More precisely, it is called A-star if the H value is computed on a um, admissible function, which is always bigger, smaller than the real cost. Okay. So by using this, we can solve it. So this is the way to solve. This is the way to implement H value, and then this is the way to implement best first search, and then we implemented A-star search to solve any 8 puzzles. So if we change NN to 3, we can show that any 8 puzzles can be solved by hitting S. Like it gives, after 61 steps, 61 tries, it gives step in 16 steps and all the way down very close to the answer. Okay, N and S. Whatever you try, it can return answer less than 31 steps. That can be a solution, but optimal solution to the 8 puzzle, like this. Okay, but then we thought that this is not good enough for solving 15 puzzles. Okay, and then we implemented, as a preparation to implement IDA star, we first implemented recursive depth first search, and then iterative deepening depth first search, and then implemented IDA star search. IDA star, the idea is good that it calculates F value just like A star and use it as a means to update the depth limit of the iterative deepening star. Okay, if you look back the program that I explained about IDA star, it is very good, wise program to calculate IDA star algorithm. And if you change this to 4, say if you change the fixed n to 4, we can solve most of the problem given these 12 slides freely. If you hit S, we can try after 64,000, get a solution of 37, which is good enough to solve it in reasonable time. For bigger problems, like smaller fixed n, it sometimes takes time, but anyway, it can solve. Okay. Then lastly, we made an auto-run demo to show 15 puzzle solutions, which was fun enough to show that it can solve and show the demos step by step. Okay. Again, let me try with fixed n 4 and solution S. Okay. After 107,000, and then type D will give a very quick view of the solution obtained by this algorithm. Great. Okay, so that's all for the summary, second part of the summary of sliding games and AI approaches to solve them. I hope if you need it, go back and see the programs again and enjoy the AI solution and game solving. Okay, I hope you like this program, and we will continue to give you more lessons about Python. Okay, that's all for today. Come back again next time. Bye bye.